All right, so first thing we're going to talk about are what we call arithmetic sequences. The word looks like arithmetic, but when we use it as an adjective, it's pronounced arithmetic. So an arithmetic sequence, I'm going to give you a couple of examples. An arithmetic sequence would be something like this. 1, 4, 7, 10. That is an arithmetic sequence. Here's another example. 6, 1, -4, -9. Those are arithmetic sequences. What can you tell me about those sequences? How am I getting from term to term here? I'm adding 3. That 3 is called the common difference. The common difference. Meaning that if you take 10 minus 7, 7 minus 4, 4 minus 1, you always get the same number. So for this one, the common difference is 3. What about this one? How am I getting from term to term in this one? I am subtracting 5 or adding -5. And so that common difference is -5. An arithmetic sequence is one in which you get from term to term by adding the same number. You add the same number to get from term to term. And that number that you add is called the common difference. Okay? Now, I want you to look at, we'll just use my first one as an example. And you don't necessarily have to write this down, but we're going to come up with a little formula so that, let's say, for some reason, I want to know the 100th term in this list. But I don't want to write out all 100 terms. We're going to come up with a formula that will allow us to find whatever term we want of any arithmetic sequence. And it's real simple. Let's look at the first one. And I'm going to use some notation here that's used when we study sequences. So the first term of the sequence, which I'm going to call A sub 1, the first term of the sequence is 1. Period. I mean, that's okay. Now, the second term of the sequence is 1 plus 3. Right? And the third term is 1 plus 3 plus another 3, or 1 plus 2 3s. So the first term was 1 plus no 3s. The second term was 1 plus 1 3. The third term was 1 plus 2 3s. What do you think the fourth term is? 1 plus 3 3s, right? 10. So in general, the nth term for this sequence right here would be 1 plus n minus 1 3s. Would you agree with that? When I was finding the fourth term, I needed 3 3s. When I was finding the third term, I needed 2 3s. So if I'm finding the nth term, it'll be n minus 1 3s. So this would be a formula for that particular sequence. Now let's check. Yes. Look, there's it comes. Okay.
This one, what's the point of putting the n minus 1?
That was my question.
Okay, as opposed to what? I mean, what would I put there instead? Because every term has a different number of 3s.
Yeah.
Would it just be n? Why can't you just put n?
Well, look at the fourth term. The fourth term has 3 3s. The third term has 2 3s. Do those two numbers match?
No.
No. So if I put n here, I can't put n here because they're not the same thing. What is the relationship between this number and this number? Isn't this one 1 less than this one?
Yeah.
So if I call that n, I got to call this n minus 1. Now, I could call this something else, but this is always going to be 1 less than that. Okay?
Okay. Thank you.
All right. Now, I need to now generalize this. I want to generalize this because, I mean, I may never see this particular sequence again. So I don't need this formula. In general, where did this 1 come from? What does that 1 represent? The first term. So in general, I'm going to take my first term, and I'm going to add n minus 1. Now what's the 3? Where did that come from? That's your common difference, right? So I'll call it D. There is the formula that will find whatever term of the sequence you want. So let's look at my second example. Suppose we wanted to find the 50th term of the sequence. The 50th term. So A sub 50. That's what that means, the 50th term. The 50th term, according to our formula, for this sequence right here, I'm doing this one. The 50th term will be the first term, which is 6, plus n minus 1, which for 50 would be 49, times the common difference, which you already figured out was negative 5. So if you needed the 50th term in the sequence, and we're going to do some word problems where you can see how this can be really a good thing, is negative 239. So you need to know this. This will be memorized right there. That's the nth term of an arithmetic sequence. Now, again, let me emphasize that. Every discussion we're having here is arithmetic. And what does arithmetic mean? It's a sequence where you get from term to term by adding the same number. If you're doing anything else, it's not arithmetic, and that formula won't work. This is only for arithmetic sequences. Okay, there is another kind of sequence that's special to us. There are zillions of sequences, but arithmetic ones are special, and then so are sequences called geometric sequences. So let me give you a couple examples of those. That's a geometric sequence. That's a geometric sequence. What do you notice about these? How am I getting from term to term here?
You multiply by 2.
I'm multiplying. So it's different than arithmetic. You get that? It's different. So I'm multiplying by 2. We call that number that we multiply by the common ratio. Because 24 over 12, 12 over 6, 6 over 3, they're all the same ratio. So in this sequence, the common ratio is 2. Okay? Now, what about this sequence?
You're multiplying by negative 3.
So your ratio is negative 3. Any sequence where you get from term to term by multiplying by the same number, it's got to be the same number, is called geometric. Okay? Now I'm going to tell you a little story. I haven't had time to tell you many stories, but this is an important one. It fits right in here. One of my very first years of teaching, I had Isaac Michael's mom as a student in Algebra 2. His mom is now a physician. She's a Notre Dame grad, one of the smartest kids I ever taught. Wonderful, wonderful family, wonderful, wonderful girl. But she walked in one day and she said, Mrs. Ford, my dad and I were watching TV last night, and they said something that just doesn't even seem possible, and we were hoping that you could help us figure it out. And I said, well, what did they say? And she said, they said that if you put one checker on the first square of a checkerboard, 2 on the next one, 4 on the next one, 8 on the next one, 16 on the next one, and so on. In other words, you got your checkerboard, and each square, you double the number that you put on it. By the time you get to the last square of the checkerboard, you will have enough checkers to reach the nearest star. And she said, Miss Ford, the nearest star is the sun, and it's 9.3 million miles away, or 93 million miles away. That just doesn't make any sense. Well, let's see. Is this a geometric progression? It is. And the common ratio is 2, right? You just keep multiplying by 2. So let's see if we can figure out what that last square would be. We need a formula. So the first term is 1. The second term is 1 times 2. The third term is 1 times 2 times 2, which is 1 times 2 squared. The fourth term is 1 times 2 times 2 times another 2, or 1 times 2 cubed. Are you starting to see the pattern here? What's the relationship between the term number and the exponent on the 2? 1 less. So the nth term would be the first term times 2 to the n minus first. Does that make sense? How many squares are on a checkerboard? Anybody know? 64. So we really just want to know how many checkers are on the 64th square. So that would be 1 times 2 to the 63rd. So let's just type that in for fun. 2 to the 63rd power. Now remember, that is not a distance. That's not like miles or something. That is how many checkers are actually stacked. So it looks like we have 9.22 times 10 to the 18th checkers. That's a pretty big number. All right, so y'all know what checkers are. You've played checkers before. Let's say 3 of them, you know how you stack them on top of each other. So let's say 3 of them make an inch. So we'll just divide this by 3. Whoops. Press the wrong button. So let's divide that by 3. So now I've got 3.07 times 10 to the 18th, and that would be inches worth of checkers. So let's divide that by 12. And now I have 2.56 times 10 to the 17th feet. So I'll divide that by 5,280. And I have 4.85 times 10 to the 13th miles of checkers. Keep in mind the sun is 9.3 times 10 to the 7. That's almost squared. Not double, it's squared. It's almost this squared, not quite. Isn't that amazing? That is a great, great story. I'll tell you one more. Again, back from the olden days, first year teacher, 22 years old. You guys, oh my gosh. I mean, if you think I'm bad now, I was terrible. I mean, it was awful. And I had this kid in class who's a great kid, good cathedral family, wrestler, very good wrestler, like state wrestler type. But he never did anything. I had him in geometry. He never did anything. And it was getting really, really annoying. So I asked the dean of students and his mom if we could have a meeting. And so we sat down and I said, okay, young man, here's my proposal for you. Back in those days when kids got in trouble, I grew up on a farm, and so we just did things differently. So when kids got in trouble, I would say, give me 10 push-ups, or, you know, go put your nose in the circle on the board, you know, that kind of stuff. But this kid, he loved doing push-ups, and he was very strong. And so he would, like, show off. He would deliberately do stuff wrong so he could do push-ups and show off, like, one-handed and clapping in between and all kinds of things. And I didn't know what else to do, so I had this meeting, And we sat down and I said, okay, here's the contract. As long as you can do 1 push-up today, 2 tomorrow, 4 the next day, 8 the next day, and so on, you don't have to do anything. You have to come to class, you're only 15 years old, it's a law, you gotta be in school, but you don't have to do anything as long as you can do those push-ups. Well, you can see and I said, but as soon as you can't do them anymore, then you have to start being like every other student. And his mom went along with it. The dean, who was not obviously Mrs. Song back in those days, it was a different person, said, are you sure you want to do this? And I said, yes, because what did I know? It's not going to be very many days and he's not going to be able to do the push-ups. I mean, for the first week it's okay, but after that, these numbers get really, really big, really, really fast. On the 10th day, just the 10th day, for example, that would be 512 push-ups. Then the day after that is 1,024. And the day after that is 2,048. I mean, it just explodes, which you can see from Kathy's checkers example. Anyway, what do we need to take away from all these stories? We need to take away the general formula for a geometric sequence. The general formula for a geometric sequence, we can get it right here. A sub n is the first term times the common ratio to the n minus first power. That is how you find whatever term you want of a geometric sequence. Okay? So now we got that. Now we're going to look at some sequences. We're going to tell what type they are. We're going to give an explicit formula. This is called an explicit formula. An explicit formula is one that you can just jump to whatever term you want. So when I wanted the 64th term, I could just go there. I didn't have to build all the ones in between. Now, what is a recursive formula? Well, we're going to talk about that when we get to it. But let's look at the first sequence. Arithmetic or geometric? Arithmetic, right? So this is an arithmetic one. The explicit formula is the first term plus the common difference, which is what? What's our common difference? 4 times n minus 1. That's the formula that you should have written down up above. A sub n equals a sub 1 plus d times n minus 1. Now, let's clean this up. So it's actually, when it's all cleaned up, 4n minus 1. That would be the explicit formula. So again, what that means is, if you want the 100th term, you just plug in 100. And you got it. That would be the 100th term. Now, some sequences, not this one, but some sequences can only be described, or can best be described, what we call recursively. And what we mean when we say recursively is you find the 100th term by doing something to the 99th term. In other words, you build it as you go. In a minute, we're going to look at one that has to be done that way. This one doesn't, but we're going to do that anyway. So in other words, what we're saying is the second term is the first term plus 4. Agreed? And what about the third term? What's the third term? The second term plus 4. So it looks like all I have to do, if you give me a term, all I have to do is add 4 to it to get the next term, right? So what that looks like is, you give me a term, any term, I add 4 to it, and I get the next term. So the term that comes after the 6th would be the 7th. And the term that comes after the 10th would be the 11th. So you give me a term, I'll add 4 to it, and I will get the next term. This is called a recursive formula. Now, whenever you write a recursive formula, you must give the starting point. Because if you don't tell me where to start, if all you tell me is I add 4, do I have any idea what numbers you're talking about? No, I need to know where to start. So when you write a recursive formula, you have to give a starting point. So this says the first term is 1. Okay, so what would the second term be? Well, according to our formula, the second term would be the first term, which is 3, plus 4. So if n is going to be, if a sub 2, if n plus 1 is going to be 2, then n must be 1. So this says a sub 1 plus 1 equals a sub 1 plus 4. So a sub 2, 1 plus 1, equals a sub 1 plus 4. Now these are not very convenient, because if I wanted the 100th term using this formula, wouldn't it be the 99th plus 4? And where would I get the 99th? The 98th plus 4, right, so Laura's going like this. You'd have to go all the way back. So these are not handy at all, but sometimes they're necessary. We'll look at one. But first, we've got another example here. B. We're going to do the same thing. Look at sequence B. Is it arithmetic or geometric? Or neither. It could be neither, I suppose.
Geometric.
It is definitely geometric. How are we getting from term to term?
Multiplying by half.
Negative 1/2, actually. Yeah, we're multiplying by negative 1/2. I heard somebody say dividing by 2, and I mean, sure, that's what we're doing, dividing by negative 2, but when we're dealing with sequences, we either add the same number, which could be negative, or we multiply the same number, which could be a fraction, okay? So we're multiplying by negative 1/2. All right, so what formula? Well, it's geometric, so our formula says the nth term is the first term times the common ratio to the n minus first. And we're not going to simplify that. Just going to leave it the way it is, just like that. That's the explicit formula. So if for some reason you wanted the 10th term, you could calculate it. That would be the 10th term. Explicit formula means you can jump right to what you want. Now, what would be a recursive formula for this one? You've kind of already answered the question, because you said in order to get from term to term, I'm going to multiply by negative 1/2. So if you give me a term and I multiply it by negative 1/2, then won't I get the next term? And the term that comes after the n is the n plus first? Now, what do I always need to include, though, when I write a recursive formula? The starting point. So our starting point is negative 2. So that all would be your recursive formula.
I have a question.
Yes?
Could you just talk about how you got that formula?
Well, when I go from term to term, I multiply by negative 1/2.
Right.
So if you give me a term, I'll call it a sub n, and I multiply it by negative 1/2, then I'm going to get the next term in the list. And the term that comes after the nth term is the n plus first term. The term that comes after the 6th is the 7th. The term that comes after the nth is the nth plus first, n plus 1 term. Now, I want to look at, I have an extra note down here at the bottom because there is a very special sequence that we need to talk about. Have any of you ever heard of the Fibonacci sequence before? The Fibonacci numbers, the Fibonacci sequence? Okay, it's really a pretty cool pattern, and it happens all over nature. So, have you ever been to those places that have fields of sunflowers and are driven by one or something? If you look at the way the seeds grow in a sunflower, unless they've been damaged or something, they grow in the Fibonacci pattern. If you're wandering through the woods and you find a pine cone that hasn't been damaged in some way, those kernels are growing in the Fibonacci pattern. This is the Fibonacci sequence. Okay, can you see what's happening? It's growing for sure, it's growing.
Adding one every 10, like it's like x0 plus 1 plus 2.
That breaks down. I mean, that works, but, so here you add 2, here you add 3, but here you add.
These are the two numbers before it get added.
That's it. That's the Fibonacci sequence. To get this number, you add these two. And to get this one, you add these two. So in other words, it is built recursively. I can't tell you what the 100th term is here, because the only way to get the 100th term is to add the 98th and 99th, okay? I do not like recursive formulas, but sometimes they are necessary. And here's an example where it's necessary. So let's see if we can write the formula. You have already determined that, let's say 1, 2, 3, 4, 5. Here's the 6th term. All right, to find the 6th term, you added the 5th and the 4th. Is that true? You added these two to get that one. So now I'm going to generalize that concept. If you give me a term, I'll call it the nth, and I add the next term to it, which would be the n plus first, right? These are consecutive terms. Then I will get the n plus second. So whatever term you give me, let's say you give me the 10th term. If I add the 10th and the 11th, I will get the 12th. That's what happens in Fibonacci. That's the pattern right there. Now, what do I always have to include to get this ball rolling? In this case, it's the first two, because I can't start building the sequence unless I have both of these, right? So for this one, I need the first term and the second term. And they both happen to be 1. But there are other sequences you could build this same way that would start with other numbers. Does that make sense to you? So I could do this exact pattern, but what if I decided I wanted to start with 7 and 10? I would get a different set of numbers, but I could say 17, 27, 44. I mean, I could use the Fibonacci pattern to generate a set of numbers starting with a different beginning. That particular one is Fibonacci. He actually, we had a book in the library, I think, or at least I bought one years ago for the library, about all the Fibonacci applications. He actually wrote about this when he was studying a rabbit population. That was the beginning of his writing about this. So if you care about that, you can go look up Leonardo Fibonacci and study that sequence a little bit. All right, got one more to go. And this one we are doing an explicit formula only. This one is hard. This one's a little bit tricky. It is not arithmetic, would you agree? And it is not geometric. But that does not mean that there isn't a pattern here. So I'm not asking you to do it recursively. That's a little bit wacky, but explicit only. So we got to figure out what the pattern is first. Does anybody see what's going on?
3, 5, 7, 9. The increase is going up to each.
Okay, so then your challenge becomes, how are you gonna formulate that? Put that into a formula. I know, that's hard. That's hard. There is something special about these numbers. If you take a close look at them, it's tricky. I mean, you haven't practiced very much, so you're not like in tune to picking up on things like this, but take a look at those numbers. How about if you add 1 to all of them? What would happen if we added 1 to all of these numbers? What would we have if we added 1 to all of them? Is there anything special about those numbers? They're the squares. Absolutely, they're the squares. So what does this represent? This represents the squares minus 1. Would you agree with me? So these numbers are the squares minus 1. So the nth term, so the first term is 1 squared minus 1. Is that true? I'm checking my formula to see if it works. The second term should be 2 squared minus 1. Is it? The seventh term is 7 squared minus 1. Let's see. 1, 2, 3, 4, 5, 6, 7. Right there's the seventh term. So this is your explicit formula.
No, you're not.
Not every sequence is arithmetic or geometric. Arithmetic has a formula you use all the time with arithmetic. Geometric has one you use all the time with geometric. But if it's not arithmetic or geometric, you have to figure it out. And you figure it out by looking at the pattern, and some of them are hard. Pattern reading is an inherited trait, so we can get better at it by practicing, but some of you are automatically going to be better than others just because you have those genes.
Mrs. Ford,
Yep.
I have a quick question.
Yep.
So, when you decided to like add 1 to like all of the numbers,
Uh-huh.
how did you know how to do that?
I recognize the pattern of numbers up there.
Okay.
I mean, that's just it. It's what I was just saying, Jacob. Pattern reading is something that we can practice, or you can practice more of. Your textbook has quite a few sequences in it. But there's no like magic wand I can shake over your head. It's just you see it or you don't. And hopefully you'll practice enough where you start picking up on that. Squares, the squared numbers are very popular in sequence land. So, I mean, I'm kind of programmed to look for squares or cubes, or sometimes even factorials, like the factorial numbers, 1 factorial, 2 factorial, 3 factorial. So if I see a set of numbers like this, I'm immediately thinking of factorials because I'm familiar with that set of numbers. So if I see something like this, I'm thinking of cubes because those are the cubed numbers. If I see all of those with 1 added to them or 1 subtracted from them, then I think about like what we just thought about. So you just gotta be on the lookout for those. Almost all of our problems are gonna be arithmetic or geometric, but you will have some random ones thrown in from time to time that you're gonna have to deal with. All right, so in number 2, we've got some explicit formulas. These are not arithmetic or geometric, they're just formulas. And it says find the first 3 terms. So we're going to find a sub 1, a sub 2, a sub 3, and a sub 50, which we can do with an explicit formula. So here we go. What's a sub 1? We're just putting in ones. A sub 1. So n is 1. So a sub 1 is 2. A sub 2 would be a sub 3 would be 4/3.
Yeah.
And a sub 50 would be 51/50. That's easy. In explicit formula, you just plug in whatever you want for n. So if you want a sub 1, you just plug in 1s. If you want a sub 50, you just plug in 50s. That's all there is to it. The formula you just built, you said was, what was it, n squared minus 1? So if you wanted the 100th term, you would just plug in 100. That's an explicit formula, the one you just made. All right, so how about this one? Again, we want the first 3 and the 50th. So what's the first one? 4/3. And the second one? 1. It's 4/4, so it would be 1. The third one?
4/5.
And the 50th one? Yeah, it'd be 4/52, which reduces to 1/13. Both of these problems that we just did are what we call convergent sequences. Convergent is the opposite of divergent. Do you know what, when we say you diverge, some people say I digress, but if two roads diverge, what does that mean? They split apart, right? They go off forever and ever and ever like this. But if you converge, you come together. So if you look at these terms right here, I'm looking at these two sequences we just examined a little bit. Can you see, look at the first one, can you see that the numbers are getting smaller? Now I'm going to ask you a very important question. Are they, if I put them on the number line, so here's 0 and here's 2, here's the first one, and these numbers are getting smaller, so like here's 1 1/2, and here's 1 1/3. These numbers are getting smaller. Are they going to keep getting smaller forever and ever and ever and ever and ever? If I keep going, are these numbers going to keep getting smaller and I end up graphing them clear out here somewhere on my number line?
Yeah.
Think so?
Yeah.
You think they're going to go past 0?
No.
Well, no, they're not going to go past 0, so I'm not going to graph them out here on my number line, right? In fact, look at this real carefully. I don't think they're going to go past 1. I think they're going to keep getting closer to 1. Think about that for a minute. I'm looking at this sequence. Why do I say that? Why do I think that? What is it about these numbers that makes me believe they're never going to get smaller than 1? Exactly. In this fraction, won't the numerator always be 1 bigger than the denominator? And when you have a number, I don't know, when you have a numerator that's 1 bigger than the denominator, isn't that always going to be bigger than 1? Now, 1,000/99, 100/99, and 1,000/999, this one is closer to 1, it's smaller, but they're not going to go past 1. Agreed? This sequence is convergent, and it converges to 1. It gets closer and closer and closer to 1. The notation we use for that, the notation we would use to tell someone else that this sequence converges to 1 is this. The limit as n approaches infinity of our sequence is 1. Now you've seen that notation before. when we were doing asymptotes, because asymptotes are limits. But this says the limit, as you let n get bigger and bigger, like I did 100, and I did 1,000, I could do 1,000,000, but I'm just going to keep getting closer and closer to 1. All right. Let's take a look at this one. What's happening with this one? Now, you told me a minute ago that it also is getting smaller. So let's examine those. Here's my number line. There's 0. The first one was 4/3. So 1 and 2 again. So here's the first term. It was 4/3. And the second term was 1. The next one was 4/5. And that one's 1/13. Tell me about those terms. Their limit is not 1, right? It went past 1. What's their limit? 0. This will never be negative. Agreed? So since that will never be negative, but they're getting smaller and smaller and smaller, our limit is 0. So we would say the limit as n approaches infinity, that is, let n be bigger and bigger numbers, just like we did, 1, 2, 3, 50. As you let n be bigger and bigger numbers, your limit is going to be 0. Now, I erased my other, oh no, I got it here. All right, we're going to
Is
connect.
it always going to be equal to? It'll never be like greater than?
Mean the value of the limit?
Yeah.
Yes, always equals.
Okay.
Okay? Now, I want to tie this to something that you already know to show you that this is going to be easy for you, or it should be easy for you. We have graphed things like y equals x plus 1 over x. And we talked about asymptotes for things like this. How did you find the horizontal asymptote? If you had to graph this, how did you find the horizontal asymptote? Do you remember?
What x can't be.
No, verticals are what x can't be. But to
Um,
find horizontals, didn't we compare the powers? So these are the same problem here. So when you put x over x, you would say your horizontal asymptote is 1. The horizontal asymptote is the limit. So you're going to find the limit the same way you did the horizontal asymptotes. They're the same thing. So for this problem, remember our rule? If the power on the bottom is bigger, there's no n up here. So what do we got? So everything, hopefully you remember about horizontal asymptotes, that's how you're going to find your limits. Now, did we have any problems that didn't have a horizontal asymptote? Yep. When does that happen?
When there's an x on top and nothing below.
Exactly, when the power on top is bigger, and those are called divergent sequences. They diverge. We said before there's no horizontal asymptote, but now we're going to call it divergent. That's our new vocabulary word. All right, so here we go. We're going to look at some of them now. Let's look at this sequence. I don't have a formula here, but I kind of do. It's n squared. Tell me about that. Are those guys converging or are they diverging?
Divergent.
That's definitely divergent. Absolutely. There is no limit. There is no limit. When you graph n squared, guys, what does it do? Yeah, it just shoots up. There's no top on that. There's no asymptote to hold that in. That just keeps going, 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 going. All right, what about the next one? It is definitely convergent. And what would you say the limit is? What's happening to those terms? Where are they heading?
To 0.
To 0. These are going to 0. So the limit as n approaches infinity of 1 over 2 to the n is 0. 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, they just keep getting smaller and smaller. Now, C looks more like what you've seen before. What would you say the limit of this is? Tyler says 3, is he right? He absolutely is. That is a convergent sequence, and the limit is 3. Because if you graph that, and you all know how to do it, you put a vertical asymptote at -2, and you put a horizontal asymptote at 3. And wherever you put the horizontal asymptote, that would be your limit. Okay, be careful with D. No, actually D has a limit. What is the limit?
-2.
Yep, it's -2, because when you put n over n, even though the problem's a little backwards, it's -2. So your limit is -2. What about E? It's definitely convergent. It has a limit. It has a limit. What would its limit be? 4/5. Remember, when you did horizontal asymptotes, didn't you compare the highest powers? So when I compare the n squareds, I get 4 over 5. So E has a limit of 4/5. What about F? F has a limit. What's your highest power?
Oh, it's 0.
It's
Zero.
0. It's 0. Because your n squared is your highest power, and you don't have any of them on the top, but you've got one of them on the bottom. So right there is your limit, and it's 0. How about G? G is divergent. G has no limit. It is divergent. Does everybody see that? You have 8n squared and 0n squared on the bottom. So when you try to compare those, it's not going to work. Anytime the power on top is bigger, it's going to diverge. Anytime. All right, so now that's all those problems were kind of the same. So now we're branching into another set of problems. So is everybody clear on that? All you people out there in virtual land, remember finding horizontal asymptotes? And the limit of the sequence is going to be exactly the same. All the rules, all the way you do it, exactly the same way. Now, when we look at H, that is a different kind of problem. I mean, it's just structured differently. It's not n over n. No, it's not n's over n's. It's something to a power, a number to a power. So I want you to think about that one and the next one. We're going to look at both of these together. And think about, okay, what would this sequence look like? So if I put in a 1, it would be 2/3. If I put in a 2, it would be 4/9. If I put in a 3, it would be 8/27. I'll do one more. If I put in a 4, it's 16/81. Now, if you're having a hard time getting a feeling for those fractions, type them in on your calculator and look at the decimals. So like this is 0.67, this is 0.44, I don't know what that is. That's 0.30 basically, and this one is 0.1 or about 20, looks like. All right, so those are roughly decimal approximations. What is happening to those decimals or those fractions? They are shrinking, right? I want you to think about it. Every time you multiply something by 2/3, doesn't it get smaller? You take 2/3 of something. So these are going to keep going And like somebody over there said, the limit is going to be 0. Because when you multiply something by 2/3, it shrinks. Now, what happens here? These are not going to get smaller, are they? These are going to keep going. These are going to diverge. Because this is 1.5, this is 2.25, this is, I don't know what, but it's 3 point something, right? They just keep getting bigger and bigger and bigger. So this one has no limit. So what made that one converge and this one diverge?
That one's bigger than 1.
Bingo.
The first one's less than 1.
That's it exactly. Both of you guys said the same thing. If the number that you're raising to the power is less than 1, then your limit is always going to be 0. But if your number that you're raising to a power is bigger than 1, then you will never have a limit. Because if you multiply by something bigger than 1, you just keep getting bigger. But if you multiply by something less than 1, you just keep getting smaller. Now, when I look at problem J, my beady little eyes focus right there on that 5/4. I don't care what the exponent is. If I am multiplying by powers of 5/4, I'm growing. No limit. The exponent is not the issue. It is the number that you are raising to a power. So J has no limit. What about K? What's its limit? 0. The limit is 0. It's not a fraction in there. It kind of is. 36 over 100, 1/9. Or no, 36 over 100. Where did I get 1/9? You know what I mean. It's 36 over 100, whatever that is. And what about L? Divergent. No limit. No limit. Okay? Now there's one more, I don't have any examples of it on there, but usually when we talk about limits in initially our first conversation, there are like 3 big categories of types of problems. One is this kind. The only difference is less than 1, bigger than 1. That's it. Either 0 or no limit. The other one is this kind of thing that we talked about before. That limit would be 1/2. And then the other thing, the other big group is, what happens if you take the limit of just a plain number with no ends in it at all, just a plain number? What do you think that is? It's 7, yep. The limit of a constant is that constant. So if you have to, when we start putting these problems together, if you have the limit of 4, the limit of 4 is 4. Okay? All right, well that takes care of that. Our bell rang, so let me make a note of where we're stopping. And then you can now do the 9.4 limit homework. So one of your homeworks pages is called 9.4 limits. So that one will be due on Monday. Okay? So your limit homework, not the first page, although you might be able to figure all that out now too. But the page that's called limits is due on Monday. Also, remember on Monday we will spend part of our time doing some practice over probability like we did the other day. Because on Tuesday you have a quiz. All right, everybody clear on all that? All right, have a great day.
Thank you.
Bye-bye, you're welcome.
Thank you.
Bye. All right. You guys want to spray your desks and wipe them down?
You think that's the same time you guys go through
guys wanna spray your desks and wipe them down?
No, I thought that was a good question. I'm not buying into that. I really don't really get out.
You don't wanna get up?
I promise I don't.
You are absolutely, I don't even wanna say it.
I don't have COVID.
You don't have what?
I do not have COVID. I promise.
Well, I know, but we still have to wipe them all down. That's the school rule.
So many Indians and so many glasses.
Yeah, it has.